Okay, so we have reactants on this side of the reaction and products on this side. Okay, the plus sign it helps us to know the things that are reacting together. The arrow separates the products from the reactants. Okay, and the coefficients that go out in front tell us the relative numbers of reactants or products that are formed. The reactants that are used, this coefficient, or the amounts of products that are formed. Okay, those would be our coefficients. Okay, so, whoops. Here we can see that this is kind of how you would see the chemical reaction occurring, right? So you have the methane molecules, and remember it was 1 methane for every 2 oxygens. Okay, so how many methanes do I have? I have 3 methane molecules. So that means how many oxygens should I have to react with that? 1, 2, 3, 4, 5, 6. Because it's the ratio, the chemical reaction is the ratio of what's happening. Okay, but in reality, you have way, way, way more than this, because I couldn't do this on this level. I couldn't actually take 3 methane molecules and react it with 6 oxygen molecules. That would be impossible. They're too small. I can't take individual methane or individual oxygen molecules and react them. So how do I react them? I react them in molar amounts. What are molar amounts? Remember, a mole is what? 6.022 times 10 to the 23rd, right? Those are the amounts that I take. Those ginormous amounts. And that's what I'm reacting. But in these ratios. So I might take 1 mole of oxygen. Nope, I'm sorry. 1 mole of methane, which would be 6.022 times 10 to the 23rd molecules of methane. And 2 moles of oxygen, which would be 6.022 times 10 to the 23rd molecules of oxygen times 2. Right? It's the same ratio. It's just in ginormous amounts of these things. So I'm not actually going to take 3 and 6. I'm going to take 6.022 times 10 to the 23rd and 6.022 times 10 to the 23rd times 2. So I'm going to take large amounts. Okay? Okay, and it's going to produce carbon dioxide and water, also in molar amounts. Okay, in these ratios, these are the correct ratios, but this is just a depiction to help us understand it. But in reality, I wouldn't just produce 1, 2, 3 carbon dioxides and 6 waters, 1, 2, 3, 4, 5, 6. Those are the correct ratios, but I would obviously produce much more than that. They would have to be measurable amounts. Measurable amounts. So I would actually produce a measurable amount of water in this reaction. And I could figure out if how efficient my reaction was based on how much I produced. So it was supposed to produce, let's say these are molar amounts. Each one of these molecules represents a mole, or 6.022 times 10 to the 23rd. So if I have 6 molecules of water, of oxygen, I should produce 6 molecules of water. Or 6 moles of water. If I start out with 6 moles of oxygen, I should produce 6 moles of water. Well, how much did I produce? Well, what if I only produced 5? In my reaction, somewhere there was some inefficiency in it, perhaps. And I didn't quite get where I wanted to. Okay? And so that's how we're going to look at these chemical reactions. We're going to be able to begin to understand, if I start out with this much, how much should I produce? And it's going to be based on the molar quantities. Okay? 3 moles of methane should produce how many moles of water? Well, if I start out with 3 moles of methane, 3 moles of methane, CH4. Okay. then I should produce, based on the ratio, that there are 1 mole of methane for every 2 moles of water produced. I'm writing too close to the top. 2 moles of H2O produced. Okay? Based on that, I should make 6 moles of H2O. Okay, and that's what this is depicting, right? If I have 3 moles of methane, I should make 1, 2, 3, 4, 5, 6 moles of H2O. This is how we're going to begin to develop these ideas of understanding how I can predict how much I should make, or to set up a chemical reaction. If I want to produce a certain amount, how much do I need to start out with? Okay, so this is really kind of the heart of chemistry, being able to know how much product or reactant you need to begin with, or how much you're going to produce in a chemical reaction. Okay, all right, so let's talk about balancing chemical reactions. So if I start out with this reaction, hydrogen and oxygen are mixed and reacted by adding heat to form water as the only product. Right, the balanced chemical equation. So what is this telling me? It's telling me I'm taking hydrogen plus oxygen to form water. And the chemical formula for water is H2O. Now, did you guys see anything wrong about how I wrote this? Okay, so I could easily just say, okay, 2 to balance it, right? But there's something else wrong. Does hydrogen exist as H2? Is that how it exists? I mean as H, just H all by itself? I'll give you guys the answer. No, it exists as H2, right? So if you ever see something that says you're reacting hydrogen with something, you need to make it H2. It's a molecule. It's an H2 molecule. It doesn't exist as a single hydrogen in nature. Okay? What else is wrong? What's that? That's right. It's O2. Okay? So just like we saw up here, right? These oxygen molecules, they are not individual oxygens. I have 2 oxygens there. But there's 6 of these, so that's 12 oxygens altogether. Okay? So 12 oxygens altogether, but only 6 oxygen molecules. But that's how I need to represent it. As, just like here, we said methane plus O2, okay? So CH4 plus O2. These are O2 molecules. So when I write my chemical equation, I need to make sure I'm putting O2. If it's asking for nitrogen, N2. Nitrogen does not exist as a single nitrogen. Okay? So you need to try to be aware of that if you're writing these reactions. Okay, so we now have a better starting point. This is how I start. Now what's unbalanced? The oxygens on the water, right? The hydrogens are balanced. The oxygens are not. So I want to remedy this. Okay, easy. Now it's a balanced chemical equation. Is that right? It's not water anymore. I can't do that. That's not water. I just completely changed what I was forming. So how am I going to balance this chemical reaction without changing the subscripts? That's right. I can only change the number of water molecules. I cannot change what it is. And if I change the subscript, I change what it is. That would be so easy if I could do that to balance these, but I can't do that because that's completely changing what I'm forming, what I'm making, okay? Or what I'm starting with. I can't do that. So the only thing I can manipulate when I balance chemical equations is the number that goes out front. Okay, so if I put a 2 here, what does that mean? How many hydrogens do I have?
4.
How many oxygens? 2. This number gets distributed, right? Because now I have 2 water molecules. I have 2 of them. That's 4 hydrogens, 2 oxygens. Now let's go back over here. It's not balanced anymore on the product side, on the reactant side, excuse me. So how am I going to balance the reactant side? Okay, I could put a 1 there, that's fine. I don't have to, but that's fine. Okay, so this is my balanced chemical equation. I need 2 hydrogens and 1 oxygen, and that will form 2 H2Os. This is my balanced chemical equation. Okay? These numbers are not in gram amounts. It's not 2 grams of hydrogen and 1 gram of oxygen that I'm reacting, right? That's not what I'm doing. This is in molecule or molar amounts. This is in mole amounts. 2 moles of hydrogen and 1 mole of oxygen. If it was in grams, this would be 4 grams of hydrogen and 16 grams of oxygen. Because, I'm sorry, that's wrong. O2 is 32 grams. Right? Those, see, that's the gram amount, but that's not how I balance chemical equations. Not by the gram amounts, by the molar amounts, by the molecule ratios. How many molecules of H2? I need 2. How many molecules of O2? I need 1. Or in other words, I need 2 moles of H2. That's 6.022 times 10 to the 23rd times 2 atoms of H2 for every 1 mole of O2, or 6.022 times 10 to the 23rd molecules of oxygen. Okay? That's the ratio that I need, and it's going to produce 6.022 times 10 to the 23rd times 2 molecules of water. Okay? That's what's happening here. That's what this chemical equation is telling me. It's not telling me the gram amounts. It's telling me the mole amounts. And that's going to be very important when we get into stoichiometry, because stoichiometry is simply knowing if I start out with this many moles of something, how many moles of another thing will I produce? If I have 18 moles of H2, how much water will I produce from that? Let's say that there's more than enough oxygen. Let's just say oxygen isn't a contributing factor because it's an excess, meaning there's more than enough of it. You burn it in the air, there's absolutely enough oxygen. So it would be 18 moles of water, right? Because for every 2 of these, you produce 2 of these. That's the ratio. 2 moles of H2O for every 2 moles of H2. That's stoichiometry. That's the heart of what we're doing here. Okay? And when we talk about stoichiometry, everybody starts to think it's this big complicated process, and it's not. That's it, right there. That's pretty easy. If I have 2 moles of, for every 2 moles of H2, I produce 2 moles of H2O. It's a 1-to-1 ratio. 18 moles of H2 produces 18 moles of H2O. How many moles of how many moles of oxygen would react with 18 moles of H2? What's the ratio? Well, I have 1 mole of O2 for every 2 moles of H2. 9 moles of O2. So if I have 18 moles of H2, I need 9 moles of O2 to react completely with it. If this was a perfect reaction, if nothing was left over in excess. Okay? That would be a perfect reaction. And I would produce 18 moles of water from that. Okay? That's it. That's all there is to it. Very simple. Just knowing the ratios and be able to convert. It's a conversion. Yes, sir?
How do you determine if it's 2 mole or 1 mole?
You have to balance the chemical equation. So the only way that I would know how to do this stoichiometry is by my balanced chemical equation. That is the only way. You have to have a balanced chemical equation. So if you're going to do a stoichiometry problem and they give you an equation, you have to make sure it's balanced, because sometimes it's not balanced. And then there's no way you're going to calculate these correct ratios without a balanced chemical equation. So the very first thing you have to do is make sure it's a balanced chemical equation. And then from the balanced chemical equation, I can determine those ratios. Okay?
Can you tell me where you got 18?
I made that up. It could have been any number. It could have been 182. It could have been 2. It could have been 4. It could have been anything. It just depends on how much you're starting with. So if I'm starting with this many moles of hydrogen, and I want to know how much water I'm going to produce, or how much oxygen I need to react with that, that's when I use this. Okay? So it's this number could be any number. It's X. It could be anything. Okay? These ratios are the things that are consistent. Okay. So nitrogen plus oxygen form dinitrogen pentoxide. Okay, so you're saying like this? Okay, that would balance it. But
oh yeah, the oxygen doesn't. Yeah.
okay, I need to start this out different. I can't. That's not right, right?
No.
What's wrong?
It needs to have the 2, right?
I need to have 2 oxygens. Oxygen doesn't exist as a single oxygen. It starts out as the stuff I'm breathing in the air right now. It's not just a single oxygen, it's an oxygen molecule. It's O2, right? So that's how I need to show it, as O2. I'm starting out with an O2 molecule.
You said the same thing for nitrogen.
Yeah, nitrogen needs to do the same thing. Nitrogen in the air is also not just nitrogen all by itself. It's 2 nitrogens in a molecule. 2 nitrogen molecules, 2 nitrogen atoms bonded together like this. That's nitrogen. N2, O2. Okay, that's how they exist. They don't exist as single nitrogens or single oxygens. So make sure you're writing it in the correct way.
So 2 in front of the nitrogen, 2 and then 5 in front of the oxygen, and then 2 in front of that molecule.
Oh, okay, so what are you saying?
A 2 in front of the nitrogen.
A 2 here?
Yeah. And then.
Okay, but that would unbalance.
Yeah, you're.
Oh, I see.
You
Okay.
put 2 over there, that's 10, 4, and then 5 in front of the
Okay, good. That's true. That's right. Now, let me tell you, if you're looking at this and you're saying, this looks a little bit tricky, okay? Let me give you a tool that you can use to balance this without much difficulty, okay? So the nitrogens are balanced, right? It's the oxygens that aren't balanced. I have 2 oxygens on one side, but 5 oxygens on the other side. So if I want to balance this, and oxygen is the only thing that's unbalanced, that makes it real simple for me, because all I need to do is say, what times 2 is 5? No, what times 2 is 5? 2.5. So I'm going to change this to 2.5. The coefficient is 2.5. Now it's balanced, right? Now I have a balanced chemical equation. I have 1 of these, 5 of these, 2 of these, 5 of these, 2 of these, 5 of these. However, if I have a half, I can't keep it because I don't set up half ratios. That is not the correct finished balanced chemical equation. This is just a tool to get me there. This is a tool that helps me get to the final answer. Okay? So what I need to do is I need to multiply everything by a number that will get rid of that half. So how much do I need to multiply everything by? 2. So I'm going to change everything. I'm going to say 2 and 2. Whoops. This becomes 5 because 2.5 times 2 is 5. And this becomes 2. Just like you said. Okay? So this is the balanced chemical equation. How many nitrogens do I have? 4. How many over here? 4. How many oxygens? 10. How many oxygens? 10. So it's balanced. Okay? So whenever I multiply everything by the same number, it maintains the balance. So I can use that half as a tool to find the balance, and then I can get rid of it by multiplying by 2 and maintain the balance. Okay? So that simply is a tool that I can use to help me do that. Okay? All right. Let's try this one. So here I have a chemical reaction with carbon, hydrogen, and oxygen. And what I'm going to suggest is that when you are balancing these, you make a list. Carbon, hydrogen, oxygen. These are the elements that I'm going to balance in this. Okay? So C2H6 plus O2 produces carbon dioxide and water. And essentially, any organic molecule like this, carbon-hydrogen molecule, when you react it with water, guess what it produces? Carbon dioxide and water, always. Okay? So we're going to start with carbon, hydrogen, and oxygen. And we're going to count everything that we have on both sides of the reaction. So on the reactant side, I'm going to put an R for that. How many carbons do we have? 2 carbons. How many hydrogens? Oxygens? 2. On the product side, how many carbons do I have? How many hydrogens? How many oxygens? 3. Okay? Now, what I want you to notice is that O2 is all by itself. So what I recommend when you have something that's all by itself like that is leave it to the end. Don't balance it until the very end. The reason for that is because I can change, just like we saw, I can change that oxygen to be anything I want it to be. Okay? And then I can multiply it out if I need to. But if I leave it to the end, I can change it to anything and it won't mess with anything else. Okay? So let's start with the carbons. Let's balance our carbons. How many carbons do I, how am I going to fix the carbons? They're unbalanced. So I need 2 carbon dioxides, right? So that's going to change my carbons, but it also changes my oxygens, right? How many oxygens do I have now on the product side? Okay, it went from 3 to 5. So this chart is just helping me keep track of everything, because when you get really complicated reactions, it'll start to get, very complicated, and you need to keep track of it. So the chart helps me do that. Okay, now let's balance the hydrogens. What am I going to do that? Put a 3 here, right? That changes my hydrogens to 6, but it also changes my oxygens. Now how many oxygens do I have? I have 4 here, right?
7.
Plus 3 more. 7 oxygens. Okay? Now, I need to balance the oxygens. I have 2 on one side, I have 7 on the other side. That's okay, because what can I do? What number can I put in front of O2 to balance those oxygens? This is why I leave oxygen to the end. I can easily balance it now. What's the coefficient? 3.5, right? 3.5 times 2. Okay? That gives me 7. No, but I can't keep it, right? So what do I do? Multiply everything by 2. Change the coefficients by multiplying them by 2. So I'm going to get 2 here. Goodness. Okay? This is going to get changed to 7. This is going to change to 6. And this is going to change to 4. Okay? And this is my balanced chemical equation. All right, let's check. Let's check to make sure it's really still balanced. Okay, how many carbons do I have on the reactant side? How many hydrogens? How many oxygens? How many carbons do I have on the other side? Okay, I have 8 oxygens here, plus 6. Okay. Wait, whoops, did I do something? Oh, that's oxygen. I'm sorry. I did the wrong thing. 14. Thank you. Hydrogens, how many do I have? 12. Okay. So everything is still balanced. Everything is still balanced, which it will be. If you multiply everything by the same amount, it's always going to maintain the balance. Now, let's say you would come out with this instead. Okay? This is still a balanced chemical equation. It's just not reduced to its lowest ratios. And it needs to be. The most correct way you're going to write this reaction, if you figure this out, and then you look at it and you say, oh, I can reduce that, then you need to reduce it. It needs to be in its lowest ratio formula. Okay? So 2C2H6 plus 7O2 produces 6H2O plus 4 carbon dioxides. Okay? This is the lowest ratio. I can't reduce that anymore. That's it, the lowest it can go. So this is the correct balanced chemical equation that I would use. Okay? Okay, so before we get to that types of reactions, let's go ahead and practice this a little. So I have a worksheet here I'm going to hand out. And go ahead and start to balance these. Okay? So before you look at the back, go ahead and try to balance them on your own. Okay? And if you're struggling, then you can look at the back, or if you want to check your answer. Okay? But if you're struggling with something, also let me know so I can come help you. Okay? So go ahead and work on those. You can work with the people around you if you want. And make sure you're doing these. I'm going to be walking around checking on you guys. Is if you have brackets, okay? So let me just do that lead hydroxide one, okay? Lead hydroxide plus HCl produces H2O plus lead chloride, okay? So here's my chemical reaction. Remember, this gets factored into those. So I have 2 oxygens there and 2 hydrogens, but I have 1 hydrogen here, so that's 3 hydrogens on that side. Okay? And I have those 2 hydrogens and oxygens. So I'm going to balance my chlorines. I'm going to put a 2 here. My leads are balanced. I have now I have 4 hydrogens and I have 2 oxygens, so I need 2 there. Okay? And now it's balanced. Okay? Now, if you have a polyatomic ion in brackets and it shows up on both sides of the reaction, like number 6, okay? So number 6, AlBr3 plus potassium sulfate produces potassium bromide plus aluminum sulfate. Okay? So what I would do when I make my chart for this is I wouldn't go Al, Br, K, S, and O. I wouldn't do that. I would say Al, Br, K, and SO4. I leave the sulfate together because it's on both sides. It's here and it's here. So because it's on both sides, I just need to balance it as a single thing. So I have 3 sulfates here, so I put a 3 in front of this to get 3 sulfates over there. Okay, that balances my sulfates. Now I need 6 Ks, I need 6 Brs, and I need 2 Als. Now it's a balanced chemical equation. Okay, so leave that SO4 together. Don't break it apart. You could, and if you did, you would be able to balance it still, but you don't need to. Okay? You don't need to do that. You could just leave that SO4 together. But that's only because it's on both sides. The OH is not on both sides in the first example. So I couldn't do that. I can't keep OH together because it's not. It broke apart. Okay? So I had to balance the oxygens and hydrogens individually. Okay. So that's the other thing I wanted to mention.